There are many different macroscopic physical properties of matter that we've been talking about in relation to intermolecular forces. For example, the boiling point and the melting point of different substances. In order to understand what's actually happening at those different points, we need to discuss phase changes. Okay? And phase changes should sound familiar from our unit on thermochem, and this diagram down below should look familiar to us from CP Chem. So we have four main phase changes that we've discussed: condensation, evaporation, freezing, and melting. What we have here is the phase change diagram for water, H2O. On the y-axis we have the temperature, so as we go up, temperature increases, and on the x-axis we have heat energy, Q, heat added. So let's say we start with a sample of water that's ice, H2O solid. It's down here at the bottom. Okay? And if you notice, this diagram shows the molecules are all densely packed, they're very close together. Let's say we start at a certain temperature here below the temperature at which ice starts turning into a liquid. As we add heat, the temperature of the substance increases. Okay? As we add heat, the temperature of the substance increases. And what that temperature is doing is taking the intermolecular forces between all of these molecules of water, and that heat that's being added is breaking those intermolecular forces. Because in order to turn this solid into a liquid, we can see the molecules have to be much more spread apart. Okay? So what is the name for that process called? Well, when we go from a solid to a liquid, it's called melting. If we go the other direction, from a liquid to a solid, it's called freezing. And in that process, it's the exact opposite. These molecules have to be brought closer together to form a more condensed, packed substance to form a solid. So what we want to be able to pull from this is the intermolecular forces are going to dictate how much heat it takes, how much energy it takes to convert a solid into a liquid or vice versa. Same thing, let's say we keep adding heat, we're heating up this liquid water, and then we get to this point here where we have a flat line, the temperature's not changing, but we're still adding heat because we're going to the right on the x-axis. So since we're still adding heat, what that heat is going towards is taking all the intermolecular forces between these molecules now in liquid and breaking those intermolecular forces further so those molecules can be even more spread apart to form this spread out gas. When we turn a liquid into a gas, that's called evaporation or boiling. And if we turn a gas back down into a liquid, that's called condensation. So you need to know those four terms: condensation, evaporation or boiling, freezing, and melting. Because the terms that we've been using in class, the melting point and the boiling point, are dictated by particular temperatures. So the melting point is the temperature at which a solid turns into a liquid. What is this exact temperature here where this solid turns into a liquid? And the boiling point is the temperature at which a liquid turns into a gas. So if we drew this over, what is this temperature here on the y-axis at which that liquid is turning into a gas? So when we start comparing different molecules together to say this one has a higher boiling point than that one, you got to visualize in your head, oh, that means these molecules, if I'm talking about the boiling point, are somewhat close together, kind of sliding around one another, and I'm adding enough heat energy to break those intermolecular forces between these molecules, whether they're London dispersion forces, induced dipoles, hydrogen bonds, dipole-dipole forces, to make those molecules more spread out to form a gas. That should sound pretty familiar. What you need to be able to walk away with are those four phase changes and definitions for these two terms, the temperature at which these things happen. But we also need to know how to interpret another diagram. So this is also called a phase change diagram. This is the phase change diagram for water. Okay? Phase change diagram. And we don't need to know how to draw these, we just need to know how to interpret them if they're given to us. So let's break down what we see first on the axes. So on the x-axis we have the temperature of the substance in degrees Celsius, and on the y-axis we have the pressure in atmospheres. And what we see here is at different temperature and pressure combinations, H2O is going to exist in 3 different states, either as ice, which is a solid, as water, which is a liquid, or as water vapor, which is a gas. Okay. So the type of things we need to be able to do are, let's say we have a sample of H2O that's at 100 degrees Celsius, and let's say about, this is not an even scale, but maybe about 10 atm. Okay. Boom. And let's say we heat it up. We add temperature. Okay, we add heat to increase the temperature of the substance, but we don't change the pressure. So if we don't change the pressure, this is going to stay on a vertical line going to the right because we're adding temperature. It's going to stay as liquid water, liquid H2O, until we reach this point. This line represents the equilibrium between the 2 phases. So as we heat up that substance, eventually it gets to this temperature, which let's just approximate to be about, I don't know, 150 degrees Celsius. At 150 degrees Celsius and 10 atmospheres, the substance H2O, the sample that we have, half of it will be in the water liquid phase and half will be in the water vapor gas phase. Okay, this is the equilibrium line. If we heat it up just a little more, we're going to cross into the water vapor phase and we're going to turn into a gas. If we cool it down a little bit, we're going to stay in the liquid water phase. So what we can tell here, since we're going from a liquid to a gas, this line essentially represents the boiling point. But what we can see now is that the boiling point is not the same temperature, at all pressures. Depending on the pressure, the boiling point changes. Here, the boiling point is about 150 Kelvin. But let's say that sample of H2O was at 1 atmosphere. Boom, right here. And then we heated it up. Now look, the boiling point is only 100 degrees Celsius. So boiling point can change, just like melting point can change, going from a solid to a liquid. Notice depending on what pressure we're at, there's a slight shift towards the right of this equilibrium line for the melting point of H2O. One cool thing to notice is what's called a triple point, which is right here. At 0.006 atmospheres and 0.01 degrees Celsius, water is in equilibrium in all 3 phases. So liquid, solid, and water vapor all exist in equilibrium, a dynamic equilibrium where they're shifting back and forth. On all of these lines, it's only in an equilibrium between 2 phases. But at the triple point where they all intersect, that is an equilibrium between all 3 phases. Another cool side note that we don't need to be too concerned with, but this is called the critical point up here. Notice this line doesn't continue on forever. So actually above this point, we don't have water or a gas. We have something that's called a superfluid. And we don't need to be concerned with that, but it's something if you want to talk to me more about or we look up a little more, we can discuss later. What you need to be able to do walking away with this today is understand if you have a phase change diagram, what do these lines represent? Okay. If I give you a pressure and temperature of water, you would have to be able to tell me, and I heat it up, you'd have to be able to tell me what temperature approximately it would boil at or it would melt at, etc. And you need to know what a triple point is.